Hello.
Hello.
Hello, everyone. Welcome to the plenary session. Let's start. Our first speaker is Antonio de Maria. The title of the talk is Higgs measurement at the Atlas and CMS. So please.
Okay. Can you hear me?
Yes.
Can you see the slides in full screen?
Yeah.
Okay. So welcome everyone. I will talk about the Higgs measurements at Atlas and CMS. So, but before going to the measurement, let's give a brief introduction about the Higgs boson in the standard model. So we can summarize the Higgs boson coupling through the other particles through this Lagrangian, which is depicted here on the slides. And what we may expect is that we get a coupling proportional to the mass of the fermion in the case of fermion coupling, while in the coupling with boson, we had a coupling strength which is proportional to the square of the mass of the vector boson. So as you can see from the plot here on the right part of the slide, where we picked all this coupling, we can see a nice linearity between all the couplings that so far have been measured. And as you can see also, we get a nice agreement with the standard model prediction over roughly 3 orders of magnitudes for the particle mass to which the Higgs boson is coupled to. So if we go briefly to how the Higgs boson is produced at the LHC, so we have 4 main dominant production modes. So the most abundant one is the gluon fusion, which you see depicted in the top left part of the slide, and then followed by the vector boson fusion. And then with the other main 2 production modes are the associated production with the gauge boson, so with the W or a Z, or the associated production with a pair of top quarks. And all the values of the cross-section that you see depicted on this slide here are for prediction for an Higgs boson of 125 GeV mass with a center of mass energy of the PP collision of 13 TeV. So talking about, we just talked about how the Higgs boson is produced. Now let's move on to its decay. So in this slide here, you will see on the left part of the slide, the branch ratio as a function of the Higgs boson mass. Of course, it's centered around the best value that we know right now, which is 125, near 125 GeV. And where the large branch ratio we have is for Higgs to BB, WW star and tau tau. However, in this channel, we have poor mass resolution in the reconstruction of the event kinematic, and we have also large background contamination. Then we have the 2 so-called golden channel, which are Higgs to gamma gamma and Higgs to ZZ star into the 4-lepton final state, for which we have lower branch ratio, but we have high mass resolution, and these are used for the precision measurement, as you will see in the next slide. While if we go to the less abundant decay of the Higgs boson, we have the Z gamma and the mu mu one, which are now becoming accessible thanks to the large run2 dataset and also to the excellent detector performance. So first measurement that I'm going to talk about is the mass measurements. So this one is the only free parameter, and once you fix the Higgs boson mass, then you can get also the other properties that I was talking about. Currently, the mass is measured with high precision. We are at the per mil level in the golden channel, so Higgs to gamma gamma and Z star, and the results to get the mass are extracted from a likelihood fit of the invariant mass of the diphoton of the 4-lepton system, and this is of course done in several signal regions to enhance the various production mode over the background. And if you look at the value of the mass, that the best value of the mass that we have right now from both experiments, you can notice that we are clearly dominated by the statistical component of the uncertainty. So we have a really good handle and knowledge of the detector concerning the systematic uncertainty. So let's start talking about the coupling and the measurement in the various decay channels. So let's start with the coupling with Higgs to gamma gamma. So in this case, as I was mentioning before, for the mass, the signal is extracted using a fit to the diphoton invariant mass. We have now the latest CMS inclusive signal strength, which is 1.12 plus or minus let's say 0.09 when you sum in quadrature all the three types of uncertainty. And now that we have an excellent knowledge of this channel, we can also perform measurement within the simplified template cross-section framework, as well as differential measurement with respect to the main event kinematic. And also, as you can see from the slide here, these two plots are concerning the measurement in the simplified template cross-section. So in the various bin in which we divide our phase space for the different production mode. And from gamma gamma, we have also the first limits on the TH production, which is pretty rare production mode of the Higgs boson at LHC. And here I just reported the observed value, and we are 8 times standard model prediction at 95% of confidence level, while for CMS we are at 14. Next one, which I would like to talk about, is the for lepton final state, so ZZ star. This is a clean final state in which the main background is slim estimate, which is ZZ. It's estimated slightly different between the two experiments. So CMS used the assimilation, while Atlas used the mass sideband. We have also the inclusive cross-section measurement in the fiducial volume from both experiments, and you can see from the results reported into the slide that we have quite a good agreement of the measurement with the standard model prediction, and the two different values of the fiducial measurement from the standard model are just because the two experiments are using slightly different way of defining the fiducial volume in which the measurement is performed. I was mentioning from gamma gamma that we have both STXS and also differential measurement. So talking about the differential measurement, you can see a nice example here on this slide in which you see the cross-section versus the reconstructed PT of the Higgs boson or the 4-lepton system. And you can actually see that we have also in this case quite a good agreement with the standard model prediction. Next one is the WW star into the 2-lepton 2 neutrino final state. So in this case, we are considering a final state with an electron or muon plus some missing ET. And the main background that we have is from WW, TT bar, and Z plus jet. And from both experiments, we have all the results in the context of the STXS for gluon fusion and for BBF, like you will see in the example from the Atlas on the left part of the slide. While CMS has recently published also the first results for the BH production. This is considering 2, 3, or 4-lepton final state, depending if you are going to check with the W or on the Z boson in the final state. And we have also the inclusive BH results with right now with the significance of 4.7 sigma observed compared to the 2.8 expected. So we are nearly to the limit of the observation of this, of the observation of the Higgs2WW in the BH production mode. So next one, we'll move about from the coupling with the boson to the coupling to the fermions. So let's start with the third quark generation. So through the TTH to the TTH mode. So from the experiments, these are the results that you see in this slide are say from 2018, both of them. But of course, I mean, the results are in good agreement with the standard model expectation, and each of the experiment was able to observe the TTH production mode, so the coupling between Higgs and top standalone. And you can see also the results of the signal strength and the observed significance on the bottom part of the slide. So now both experiments are reperforming the measurement with the full run 2 dataset. And then we will move on to the combination similar to what you see here. So we might expect in the near future to have this similar, let's say, way of depicting this kind of results, but of course with more up-to-date and precise measurement. Similar when we talk about the Higgs to BB, in which in these cases both experiments are observing this decay channel and combining all the different production mode. And even in this case, the results, as you can see from the combined results, are in good agreement with the standard model expectation. And worth to mention that also Atlas has updated some of these results with, for example, a measurement dedicated in the BBF or in the boosted regime, or also there are available some differential and STXS measurement from the BH channel, which is the main channel for targeting Higgs to BB, thanks to the to the good opportunity to reject the background when you ask the V to decay leptonically, similarly to what WW was asking. Next one I will talk about is the measurement into the tau-tau final state. So from Atlas, we have a recent publication with inclusive measurement. And you can also see that the results are in quite a good agreement with the standard model. And also Atlas has observed the BBF production mode with a significance of 5.3 sigma observed, while we have only evidence from the gluon fusion production mode with roughly 4 sigma. On the other side, the CMS has performed also an inclusive fiducial measurement, so slightly different with respect to what Atlas is doing. And the results reported here are summing over the different NJet beams. And you can also see, in this case, quite a good agreement with the standard model. And also from CMS, we have the first results for the differential measurement. So next one, moving from the say third generation of quark and leptons, for which we have already observed these processes, to the next target, which is the coupling to the second generation. So let's start with the Higgs to CC bar. Here we want to probe the coupling of the Higgs with the second generation quark. And even in this case, we are targeting mainly the BH production mode, similarly to what has been reported with the other channel. So, and this is quite challenging measurement because, I mean, it's not so easy to have a good sample of C-tag jet and having at the same time a really good rejection of the B quark background. And in fact, this is quite challenging analysis because this V plus AB flavor is quite, as you can see also from the figures, quite important background. And we have so far the cross-section limit on this channel. And worth to point it out that the results that you see on the bottom part of the slide are with different luminosity. So Atlas is using the full run-2 dataset, while CMS is only using the partial one, so 36 invents femtobarn. Important is also because this measurement can help us to put limit on the KC, so the coupling modifiers of the C quark with the Higgs coupling. And so far, this is a direct measurement. And through this measurement, it's a direct way of probing this KC parameter, which is better, if not competitive, with the limit that we can get from the differential measurement through the loops from gamma gamma or ZZ. Next one is, let's move on to the second generation of leptons, so Higgs to mu mu. So in this case, we have dedicated signal region for each of the main Higgs boson production mode, and we use multivariate discriminants to enhance the signal over the background. And the results are extracted from a fit to the dimuon invariant mass, as you can see on the top from the top part of the slide, in which we have a falling background spectrum from Z mu mu, and which we expect a shoulder from the Higgs signal. And current results show that we have almost the evidence for Higgs to mu mu coupling. So Atlas has 2 sigma observed, while CMS has 3. And as you can see from the value of from the scan of the mass that you see on the left plot, these 3 sigma are obtained for a Higgs boson mass of 125.38 GeV. So next one is for starting now to search for really rare decays of the Higgs boson. So this is for lep-lepton, lep-lep plus gamma final state. So in this case, we are considering Higgs to Z gamma, which goes and later with the Z going into 2 leptons, or from gamma gamma star in the same final state. And we have enhanced the enhance of the gamma gamma star is when the MLL is less than 30 GeV. In this case, the categorization for enhancing the signal over the background is done both with cut-based and multivariate approach, and the results are extracted from a fit to the MLL gamma distribution, as you can see from the bottom plot of the slide. And currently, Atlas is also showing evidence for this process with 3.2 sigma observed with respect to the 2.1 that we were expecting. So now that I talked about all this kind of measurement, we can also try to combine all of them and of course get the best statistical power, combine different channel and different production mode. And to combine them, we interpret the results in the so-called kappa framework. which expect the Higgs boson interaction, express the Higgs boson interaction through multiplicative modifiers to the standard model cross-section and width. And as you can see from the plot in the bottom part of the slides, in which all different coupling modifiers are measured simultaneously, all the results are compatible with the standard model one. So we are in quite good agreement. And also worth to mention that Atlas has also updated results with the EFT interpretation of combining results from ZZ, BB, and gamma gamma. So after combining all of this, we can also start searching for this. We can also move on to the CP measurement in the Higgs sector. So as you may know, the Higgs boson is a CP even state. Nevertheless, a CP odd component or a CP mixture, like in the case of the kaon, is not completely excluded, and we can search CP violation in the or through bosonic couplings, in which we consider dimension 6 BSN couplings, which are CP mixed, or in the Yukawa coupling, so with the fermions, in which we can consider dimension 4 with standard model-like couplings with the CP mixed. So I'm not going into the details of all the CP measurement. I'm just listen here several of the CP violation searches into the Higgs sector by both Atlas and CMS. And just from the plot that you see in the slide on the right part of the slide, these are the coefficients of these operators here that we can access experimentally. And as you can see, these are the CP odd one. And you can see that unfortunately these are all compatible with 0. So there are still no sign of the CP violation in the Higgs sector, which will lead us directly to BSM physics. Next item, which I would like to talk about, moving from single Higgs searches to di-Higgs searches, is we know that the Higgs boson potential, the Higgs potential is influenced by the trilinear self-coupling of the Higgs boson, and the direct way to measure this, the coupling modifiers is to search for the di-Higgs boson production, and this is mainly through gluon fusion and vector boson fusion. And for gluon fusion, this provides most of the sensitivity to the self-coupling modifier. So this is called kappa lambda, which is this parameter lambda HHH compared to the measured one compared to the standard model prediction, while the VBF is a unique way to probe the BBHH vertex, as you can see on the Feynman diagram in the right part of the slide. So we may expect for the cross-section at 125.09 GeV and for PP collision at center of mass of 13 TeV, cross-section of 31 femtobarn from gluon fusion and really small one for BBF. So I will show you to the next slide several of these, the final state in which the di-Higgs are searched, but still, unfortunately, we have not observed this production. First one, which I would like to talk about, is the di-Higgs into the 4B final state. So this one has the largest branching ratio among all di-Higgs decay channels, but at the same time, it has the largest background, mainly coming from QCD and TT bar processes. And we currently have limits on both the kappa lambda and the kappa 2b, the two parameters which have been introduced into the previous slide. So all these results that are quoted here and also into the next slides are 95% confidence level. And worth to mention that from CMS, we have two different analyses targeting the 4B final state. So the first one is the one searching for resolved jet, while the second one is in the BBF in the boosted regime, where we cannot anymore resolve a single jet, but we go to a so-called large R jets. And also, CMS has also established some limits on the cross-section, which is 3.6 times the standard model observed compared to the 7.3 expected. Next one I'm going to talk about is the BB plus leptons final state. So in this case, we are aiming for one Higgs decaying into BB and the other one in WW or ZZ, and also in the total final state concerning Atlas. In this case, the main background is from TT bar and also single top production. And again, from both experiments, we have limits on the cross-section, which are 40 and 30 respectively for Atlas and CMS, times the standard model concerning what we observed. And also CMS uses these results to establish limits on the kappa lambda value, which is between -9 and 14, always talking about the observed limits, which you can also see extract from the plots into the slide. Next one is BB gamma gamma. So this is kind of low branching ratio if you consider also the single Higgs boson decay that I was talking about at the beginning of the presentation, but this is a really clean final state. So in this case, the results are extracted from a simultaneous fit of all the signal regions, and Atlas is fitting the diphoton invariant mass, while CMS is fitting diphoton and dijet invariant mass. So it's a 2D fit. And of course, like in the other channels, we have also a limit on kappa lambda and K2V, which are shown here into the slide. And also we have the cross-section limit, which are 4.1 or 7.7 by Atlas or CMS, always like talking about observing the limit. So latest one that I would like to mention is BB tau tau. So this is a final state with sizable branching ratio. If you consider the B and the tau, which are the most abundant, one of the most abundant couple of the Higgs boson decay, and we don't have an overwhelmed background. So the analysis in this case is performed in the cases in which the di tau final state, one tau goes leptonically and hadronically, or both taus decays hadronically. And in this case, the signal is extracted in Atlas from a fit to a multivariate discriminant, so a PDT, while in CMS is from the fit on the reconstructed mass. And also worth to mention when we compare the limit on the cross-section, that Atlas has published with, results with the full run-2 dataset, so 139 events per Toban, while CMS has published also with the partial run-2 dataset. So that's why you see a strong difference between the two experiments when we compare the limit. So going to summarize all the Higgs searches so far. So here you have two nice plots from Atlas and CMS. So looking at the plots, the first entry of the plots is from the combination with the partial run-2 dataset by both experiments. And the entries in the bottom part of the plots are from the single measurements that I was talking about into the previous slide. And what we can get is that if we look at the current limits, so the new limits from single analysis with the full run-2 dataset are already better than the combination with partial datasets. So this is quite encouraging results, that new exciting results are coming from the Higgs searches, or will come to the Higgs searches. So going to conclude, I just shown you an overview of the Atlas and CMS measurements of the Higgs boson. All the main production processes and decay channels have now been established. So we observed, for example, the third generation fermion and bosons. We observed all of them more with 5 sigma of significance. So now our attention is going to the second generation of fermions, so X2CC and X2mu. We have also many different differential measurements, which are covering large part of the kinematic phase space. And also, last but not least, we have quite promising results from the Higgs searches. That's all, and thanks a lot for your attention.
Okay, thank you. Any questions?
Hello?
Yes, hi, Antonio.
Yeah,
Can you hear me?
I have a question about coupling modifier plot. Here, this is. And on the left-hand side, there is two plots. And what is the difference? In the left-hand here?
This one. The difference between these two, you mean?
Yeah, yeah.
Is that the, if I remember correctly, there are slightly different hypotheses between these two plots. So you can see that in one case we have branching ratio BE and BU equal to 0, while in the other cases probably this is not the case. So it's just a different There are just different hypotheses that you do when you do the combination.
On the right hand side, the all parameters are free.
I guess so.
On the right hand.
I should check better, but I guess so.
On the left hand side, these two B's are assumed to be zero.
Yeah.
Okay. Thank you.
Hi, Antonio, can you hear me?
Yes.
Do you have any comment for the off-shell Higgs studies? High inert mass?
So I didn't put on the main part of the study, but I mean for off-shell, we can use the off-shell measurement to constrain the width measurement. And here are two results from Atlas and CMS, and you can see the best value of the width so far. I mean, we just can use the off-shell measurement to measure the width of the Higgs, which is also not predicted by the standard model.
Okay, thanks.
I have one more question.
Okay, please.
Again, the coupling modifier result. Yeah, on the right hand side, you show CMS result, and then the kappa W is central value is -1.
Yes.
Kappa W, and then there is a small bar on the around 1 + 1.
Mm-hmm.
And maybe there is something wrong in CMS analysis.
Well, I won't say something wrong. It's just that when you combine all the measurement, probably, I mean, that worth to mention also that you can see from the luminosity that this is still not the most updated measurement that we can have from both experiments. So this, you can say it's an intermediate results in waiting for performing the combination with more updated results from each measurement.
Okay. On the Atlas data, kappa W is around 1 + 1.
Yes.
Yeah. Maybe after all, CMS kappa W would be +1, I think.
I mean,
after all,
you would expect that if everything is standard model, like the expected value of the K should be 1.
Yeah. Okay. So we wait. Okay, thank you.
Yes.
Okay, thanks, Antonio, again. Let's move to the second talk. The speaker is Rona Nayak.
Can you hear me?
Yeah. The title is Beyond Strand Model Searches at Atlas and CMS. So please.
Can you see my slides in full screen?
Yeah.
Okay, thank you. I'll be giving up results for the BSM Higgs searches at Atlas and CMS. So as you know, BSM Higgs searches is also an important aspect of the Higgs physics program at LHC, in which is complementary to the measurements of the properties of the observed Higgs boson, which we just had in the previous talk. You have already seen the plots shown here and discussed in the previous talk. So I'll discuss about the BSM searches only, and the BSM searches in this case includes the searches for the more complex Higgs sector, which predicts additional Higgs bosons, and also searches for exotic decays which are not expected within the standard model. So there are many such searches in Atlas and CMS, but I'll only highlight only a few recent ones. So let's first discuss about the extended Higgs sector. The most important one is the search for the Higgs boson in MSSM, which is the most promising extensions of the standard model. So in MSSM, we have two Higgs doublets, which results in 5 physical Higgs bosons, 3 neutral and 2 charge Higgs. So the MSSM Higgs sector is controlled by 2 parameters at the level, mass of the A boson and the tan beta, while other SUSY parameters are important at a higher order corrections. There are many searches in all possible decay channels. For the high tan beta region, the most important ones are the Higgs decaying to pair of tau leptons or also pair of B quarks. For the low tan beta regions, the decays like Higgs going to pair of vector bosons or pair of standard model like Higgs boson are important ones. And there is also searches for high mass regions where Higgs decays to a pair of top quarks and also charge Higgs searches, which I'll come later. Just to mention that whenever you see a pair of fermions, you just assume that they are particle and antiparticle pairs. Okay, so this is the summary of the searches for the Higgs boson in MSSM interpreted in a HMSSM scenario. So you can see that the large part of this parameter space is already excluded. So for example, in this, the gray ones are coming from mostly from the Higgs to tau analysis. And the lower ones are coming from this low tan beta ones are coming from the mostly vector boson and other analysis. And the remaining parameter space currently is in this region. And similar interpretations are there also from CMS. Here you can see, but these results are still with only 2016 data, and the results with the full data is still awaited. But you can see that there are also interpretations in alternative MSSM scenarios for HMSSM, and also there is another scenario called MH125. So then we can go to the searches for heavy Higgs, which decays to 2 Higgs bosons, where one of these Higgs can be the standard model like Higgs boson, while another one called HS, which would be the mass of which is the difference between the mass of the heavy Higgs and the standard model like Higgs boson. Here the H can decay to pair of tau leptons, and this HS can decay to pair of BZs. So this kind of searches are motivated by models like next to MSSM, and where the MSSM Higgs sector is extended by one more singlet field. So you have additional bosons which can be lighter than the standard model like Higgs boson. So for this analysis, the events are categorized into 3 categories in terms of how the tau lepton decays. Whether it decays lepton to the leptons or decays hadronic. Okay, so you have tau E tau hadronic and tau mu tau hadronic and both tau hadronic. And then the analysis is based on the neural network based classifier, where this network output distribution is used to feed to extract the signal. The major backgrounds in this analysis is coming from the G boson plus Js and TT bar plus Js. And these most of these are actually estimated from data. So for example, the events with the real hadronic taus decay are estimated using so-called tau embedding method in the G2 mu events. And then similarly for the events where the hadronic tau is misidentified is estimated using effect probability method, and a small portion of the background where the tau decay to leptons is estimated from MC, a Monte Carlo simulation. So you can see, for example, the output distribution of the neural network in signal categories in all 3 final states. So you can see the backgrounds and the data, and the signal is close to 1 in all these cases, as expected. And so here we don't see any excess in events. So we set upper limits on the cross section times branching fractions. So here you see the upper limits on the cross section times branching fraction for different values of the heavy Higgs, which range from 240 GeV to 3 TeV, and different values of the mass of the HS, which range from 60 GeV to order of 2 TeV. And the same plot is shown in 2D in the right side. And you can see that this shaded region is the one where the limit is already below the maximally allowed values expected in the NMSSM. Okay. Okay. Then another analysis is, for example, the resonant production of the Higgs boson, where both Higgs decays to a pair of B quarks. For example, a heavy Higgs can go to decay to 2 pair of 2 standard model like Higgs, and then they decay to 4 BJs. So this analysis has 2 complementary channels. One is resolved, where all the 4 jets are reconstructed individually and then boosted, where the jets from Higgs are merged and become a large radius jet. Okay, so in this case, the backgrounds are mostly dominated by QCD, which is estimated from the lower number of beta events in data. So here you see, for example, the distribution of the di-Higgs mass, and you see the Pauling spectrum, and the background is similar to the as expected from data is similar to as expected from background, and you expect the signal as seen in this page. And as you don't see any excess, we obtain the upper limit on the cross section times branching fractions. So here you see the upper limits as a function of mass of the heavy Higgs boson, okay, or heavy mediator particle. And here you see that there is an overlapping region from the resolved and boosted region, which is in which around say 1 to 1.5 TeV. Okay. Another similar analysis is again the resonant production of di-Higgs, where one Higgs decays to pair of B quarks, but the other one decays to pair of tau leptons. So in this case, again, the events are divided according to the tau decay channels, tau decay modes. So whether tau decay is leptonic or hartonic. In this case, the backgrounds are again T-bar plus jets, G boson plus jets, and QCD. So the real hartonic tau backgrounds are modeled from MC, but the normalizations are obtained from a control region in data and also the low score signal regions. And events with fake or misidentified hartonic tau leptons are estimated from data using similar fake probability method. So this is again also based on a multivariate analysis method, where a parameterized neural network is used, which is parameterized as a function of the mass of the intermediate explosion. So the signal is obtained by simultaneous bin maximum likelihood fit to the MV output distributions in all the 3 signal regions, and also a background control region using the dilepton mass distribution in the G plus jets control region. So here you see, for example, the neural network output distribution for one of the signal points at 500 GeV. So you expect that the signal will be close to 1 while the background is close to 0. And you see that the data is very close to as expected from the background. So so you obtain the exclusion limits. There's exclusion limits on the production cross section times branching fractions. So as you see here, and there is a small excess here, which at local significance of 3.3 sigma, while global significance of 2 sigma. Okay. So there, this is a summary of Higgs to heavy Higgs to light Higgs searches or pair production searches, Higgs pair production searches, and you can see that. So most of them analysis are actually 2016. So here the updated ones are these 2 ones, 4B and BB tau tau, coming from full round 2. And you can see that the one, this blue and deep blue and light blue ones are better than the 2016 combined with result from the 2016 data, which is in the black line. And similar plots are there from CMS, but all of them are from the 2016 data. So we expect to have updates very soon. Okay, now let's come to the charge Higgs searches. So again, the charge Higgs are expected, both singly and doubly charge Higgs are expected in many models like a 2Higgs doublet model, 3Higgs doublet model, Higgs triplet models like say type 2 SUSY models and so on. So we have many searches again at LHC. These are listed here, and I will highlight some of these which are more recent ones. This is the search for the charge Higgs boson, for a light charge Higgs boson, which is coming from the decay of the top quark, and then the charge Higgs decays to CB bar. The major background to this is again the TT bar background, where the W can decay to 2 jets. So the final state here is a 1 lepton plus 4 jets, but with the 3 beta jets, 2 coming from top decay and 1 coming from the Higgs decay. And again, as I said, the major background is TT bar plus jets. And in this case, the signal and background discrimination is performed using a neural network classifier, which is trained against the standard model TT bar background. And the parameter is again as a function of the mass of the charge Higgs. And for the training, all the signal samples are combined together. So here you see a classification of events which are divided based on the number of jets and number of B-jets. And the different colors shows the fraction of backgrounds expected in different categories. So yellow is the non-TT bar background, one rest all 3 are other TT bar backgrounds. So here you see the distribution of the neural network score for a signal of 130 GB. So as you can see that the signal and background, some of the signal and background is pretty close to the data in this case. So, and we obtain the upper limit on the branching fraction of the top going to charge Higgs and charge is going to CB. So you see the limits are very strong now, and there is a small excess here again of the order of 3 sigma local significance and 2 sigma global significance. So we expect we'll see what happens with the more data. And there are also 3 theoretical predictions from 3 Higgs doublet models with 3 benchmark values, which are shown here. Okay, a similar search is also performed at CMS, though the CB charge Higgs to CB analysis is not yet complete. There is another analysis of the charge Higgs to CS bar. So similarly here the charge Higgs is originated from top decay and then decays to C and S bar. And here so the final state is exactly same as the TT bar standard model TT bar with 1 lepton, 4 jets and 2 beta jets. So in this case the idea is to search the dijet mass spectrum. And to get the good dijet mass resolution, the full TT bar events are reconstructed using kinematic fit, which improves the dijet mass resolution. And the signal region is also categorized based on the C tagging working point. And then you obtain the upper limit on the again branching fraction, upper limit on the branching ratio for the top going to charge Higgs. And you see that we are have now quite a strong limits on this branching fraction with only 2016 data, and this is again expected to be updated with the full run to data. And the third one is a charge Higgs decay to vector bosons. So you can expect that a doubly charged Higgs produced in a vector boson fusion method and then decaying to a pair of same sign double bosons, or a singly charged Higgs again produced in a BBF production mode and decaying to a Z boson and a double boson. So such kind of process is expected in models such as like Georgi-Markasek model with the SU2 scalar triplets. So this kind of signature is quite clean, as you expect that you have 2 isolated same sign lepton or 3 isolated lepton with 2 BBF jets. So it gives a quite clean signature. And then signal is extracted using a bin maximum likelihood fit over 2-dimensional distribution of the dijet mass coming from the BBF jets and the empty distribution of the 2 vector bosons. So here you see the results in terms of the upper limits on the branching fractions, sigma times branching fractions, and this is for the as a function of the doubly charged Higgs mass, and this is on the singly charged Higgs. And this is also interpreted in a benchmark scenario. So in Georgia-Makasek model, so you can see that the limits are obtained in terms of a mass of the H5 boson and sin theta H parameter. So you can see that a large part of the sin theta H parameter is now excluded. Okay. Now let's come to the non-standard decay of the standard model Higgs boson. So as you saw in the previous talk, so we see that now, as you know, that the width of the standard model Higgs is small. So you expect that even if there is small coupling to BSM, this can still result in detectable branch refractions. And with the current combination of Higgs boson measurements, there is still, it allows order of 10% decays into undetected particles, as you can see here. So this is with both invisible and undetected 0. And when you allow them to be floating, so you allow that their value order of 10%. So we expect some, there can be some non-standard decays for the Higgs boson. So we search for various non-standard decays. So one is, for example, Higgs decaying to 2 lighter Higgs bosons called a boson. So this kind of search is motivated in an MSSM Higgs scenario, where you have MSSM Higgs sector is extended by one more singlet field. So you have additional Higgs bosons. One of them can be lighter than the standard model like Higgs boson. So the search here, the H2AA decay mode is basically where A stands for just a Higgs boson that could be either scalar or pseudoscalar. So we have many such final states, and searches are performed in all possible final states, where I can decay to various final states. And the final states are also analyzed for varying mass of the A boson up to half of the standard model Higgs mass. But these analyses are quite challenging because the decay products of A boson can be sometimes boosted when the A is very light, and so special care is needed to reconstruct and identify leptons and the jets. Okay, so I will again present a few of these recent results. So one is the Higgs decaying to 2A boson going to 4 photons. And so here we look for 4 isolated photons in the mass range between 15 GeV to 60 GeV. In some models, this branching fraction can be large, and but the advantage of this channel is that there will be very low background. So in this case, a BDT classifier is trained to distinguish signal from 4 gamma background. And this BDT is parameterized as function of the hypothesized mass of the MA. So to extract the signal mass of the 4 gamma is fitted, a distribution is fitted to the data. So here you see for example, for one mass hypothesis of 15 GeV, the distribution of the data and the expected background. A background plus signal, and similarly for mass 50 GeV, and you see also again data and the expected signal plus background. So no so much excess is seen, so you obtain upper limit on the cross section times branching fractions, which is now quite stringent with full run to data. Okay. A similar analysis performed also in Atlas, where Higgs decays to 4 leptons via 2 dark sector bosons. So this is motivated by dark matter models with a scalar or total. So for example, a Higgs can decay to a Z boson and a dark Z boson, and or can both dark Z boson, or Higgs can decay to 2 scalar or pseudo-scalar boson, and in the final state you get 4 leptons. So you search for 4 leptons, and the analysis is using both electron and muons, but for high mass it uses both electron and muon, but for low mass searches it is using only muon. So you can see, for example, here the average dilepton mass for a high mass signal search region. So you see what the expected background and data distribution and what is expected from the signal for different mass values of the dark boson. And not much excess is seen, so you expect obtain upper limit on the cross-section times branching fractions, upper limit on the branching fractions. And you see here the expected line, and this is the observed ones. A few fluctuations are seen. So this is only for this final state, but there are also limits set on other channels. Okay. Another such is the Higgs going to BB and mu via two A bosons. So again, this is based on the BDT, where the BDT is trained for each 8 GeV mass window. And there again, the TT bar and Drelian are the two major backgrounds, and they're estimated from control regions. And there is an innovative idea used to reweight the Drelian background in the control region, which is in the 0 beta region, to go to the 2 beta region using a BDT-based reweighting method. And this here you see the distribution of the dimuon mass being centered for expected background. Yellow is TT bar, and the blue is the Drelian J, Drelian plus jets, and the data.
2 minutes.
Okay, thank you. So you can see here the results. So the results are obtained in terms of upper limits on the branching fractions. So here you see that the results, the expected and observed limits are pretty close, except in a one point around 51 GeV, where you see a local significance of around 3.3 sigma and a global significance of 1.7 sigma. Okay, this is the interpretations of all the Higgs to AA searches. So there are many searches. The latest ones are this Higgs to BB mu with full round 2 data. So you can see that we are closing the gap in terms of its cross-section times branching fractions. Okay, a similar, so this is interpreted in two Higgs doublet model plus singlet type, with type 2 and tan beta equal to 2. So other interpretations are also available in other scenarios. So another search is Higgs going to BB plus invisible. Here the Higgs is produced in association with the Z boson, so you can tag the Z boson in the dilepton final state. Then Higgs decays to A boson and neutralino. So here the TT bar and Z plus Z backgrounds are suppressed using these cuts like PT of the Higgs over PT of the Z and BZs. And the search is performed over the dij mass peak coming from the A decays, and you get obtain the limits again on the cross section times branching fractions. And here you see a distribution of the dij invariant mass, what is expected from background and what is seen from the data and what is expected from the signal. Okay, another search is also there for the Higgs decaying to long-lived particles. So here, this search is motivated by hidden sector models, which predict exotic Higgs decaying to long-lived particles. For example, so this phi can be standard model like Higgs boson or lighter or heavier Higgs boson, which decays to two long-lived scalars, and then they decay to 4 fermions. And in this case, it's taken as jets. So we expect decay vortices, secondary vortices in the region between 3 meter and 14 meter, which is reconstructed in a muon spectrometer. So there are dedicated methods are used. For example, a dedicated trigger to identify these events, and a dedicated reconstruction for the secondary vortices in the muon detector. And so you see, for example, efficiency for the trigger and muon vortex reconstruction efficiency of the muon spectrometer as a function of the decay length of the long-lived particles in transverse plane. And we expect 0 events are observed with this selection, while 0.3 events are expected, and a strong limit is obtained on the cross-section times branching fractions. Okay, so the last one is the search for the lepton flower violating decays. For example, searching Higgs going to E tau or mu tau decays, which is not expected in standard model but allowed in many BSM models. So there are 2 decay modes used, hadronic tau decay mode or leptonic tau decay modes, and then the events are normally categorized based on the number of jets and the vector boson fusion topology to enhance the contribution of different Higgs production methods. And this is again based on the BDT boosted decision tree classifier. So you can see the ability discriminant distribution. So here is the signal, and this is the expected background and data. The limits are obtained on the branching fraction. So the limits on Higgs going to mu tau is less than 0.15%, and Higgs going to E tau is less than 0.22%, which is then translated or interpreted in terms of echo couplings. So you can see that the limit on echo couplings is the order of 10⁻³ for both. A similar analysis is also performed in Atlas for Higgs going to E mu decays. And here again, you can see the mass distribution of the E mu pair. So this is the blue line is expected background, and the points are the data and what is expected from a signal. In this case, from the 120 GeV signal. And the upper limit is obtained again on the branching fraction. So here you see the updated upper limit on the E mu channel from full round to data, which is less than 0.01%. And this is again interpreted in terms of echo couplings, which is the limit is of the order of say 10⁻⁴. Okay, so that brings to my summary. So there's a rich program to search for new physics in Higgs sector at LHC. Both Atlas and CMS experiments search for many non-SM decays of the observed 120 GeV scalar, as well as presence of additional Higgs bosons. There are many improvements in the analysis techniques for the full round 2 analysis. So the results are improved significantly. And large parameter space of the MSSA benchmark scenarios are already explored, and there are many analyses still ongoing with full round 2 data. So we are looking forward to exciting results in the future. Thank you very much.
Okay, thank you. Any questions and comments? Okay, please.
Hi, I'm referring to your search for resonant di-Higgs production. You said that there was like a local 3 sigma axis and the BD tau tau channel. It seemed to me that there was also an axis at more or less the same location in the 4B channel, just above 1 TeV. With
this one?
That one, right. Are they consistent under the hypothesis that both come from the decay of 2 standard model-like Higgses?
Yes, but I'm not sure that the consistency check has been made, but it doesn't show much difference in this case, though. I would refer if there is any Atlas people there who can comment on this. But I think we need to wait for probably more data to see if there is still there. Yeah, but in this case, actually, there is 2 different analyses, which is a merged, the resolved and boosted together. So in this region, it's complicated, I guess.
Thank you.
Any more questions?
Hi, Arun.
Yes.
What is the number of events corresponding to that BV tau tau final state where you report that 3 sigma axis?
So I don't remember the number of events. I think I need to check papers.
Okay. Is it available in the paper? The number of events?
I need to check. I'm not sure, actually. I'm not sure.
Okay. Thank you.
Okay, so Naya, let us move to the third talk about the other searches of Atlas and CMS. The speaker is Richard Mazzini. It seems he's not online. So
maybe we can consider the next one.
So we just start the next talk.
Yeah. Luigi
Okay.
Longo. Yeah.
Okay. Well, let's move to the next talk. Luigi Longo talking about the SUSY squawk Gluino searches at large atlas and CMS. So.
Hello, can you hear me?
Oh yes.
Okay, just a second to share this. You can see the slides in full mode? Okay, thanks a lot. Okay. So in this presentation, I'll give you an overview on the Squawk and Gluino searches in Atlas and CMS. And as you know, these are largely investigated because of the larger cross-section, and in all the searches that I will show you, the simplified models has been assumed for as benchmarks for the analysis. And on all of the signal models, there was the conservation of the parity. Depending on the signal models, Squawk and Gluino masses have been excluded to the TV regime. So to increase the sensitivity or at higher masses or to close the gaps, there were different approaches and techniques that have been used and developed. There was the one looking at the top W tagging technique. So depending if the decay of the top quark are in boosted or fully partially merged or fully merged, it would be possible to reconstruct a top-like jet with an interpretive algorithm having a cone of 0.8 jets. Also, it was possible to reconstruct a W jets for with these large jets with a cone of 0.8. Or in the case the system was unmerged, the idea was to have 3 jets, for example, in the final set. In all these cases, we are assuming that the hadronic decay of the W. There were also soft-to-bit tagging technique, which were able to reconstruct B jets coming from a big quark with a PT lower than 20 GeV. The new variables like the transfer missing energy significance, that is a quantity that define or give us the possibility to define a genuine missing energy coming from a weakly interactive particle. They were also used machine learning technique to enhance the differences between the background and the signals. Or in some cases, there was also the search started to look at a different final state, as the case where there is the S-bottom production, where we have this bottom decay in B and neutralino 2, and then the subsequent decay of the neutralino 2 in Higgs boson and neutralino. While in the previous round of the analysis, the search was looking at the Higgs decay in 2 quark. In this case, in the second round, there was the analysis was focusing on the tau decay of the Higgs boson. But also there were also results showing that the enhancement in the sensitivity thanks to the combination. So several signal models have been considered, and usually the lightest SUSY particle was has been assumed to be the lightest neutralino or the gravidino. And in general, the analysis strategy is optimized for similar final state. In this presentation, I focus on for concerning the CMS on the searches for stop in Gluino in a fundamental final state, stop search in a 2-lepton final state. The combined results of the stop search that were obtained consider the final state with 0, 1, and 2 leptons, and the Gluino score search and bottom search in a final state with the 2 opposite sign 7 flavor leptons. Concerning Atlas, instead, there will be the Gluino search with a 4 and jet multiplicity in the final state, stop to stop search, and then the bottom search in the first case with the taus and big quark in the final state, and there's one case where we have only the big quark in the final state. So let's start with the CMS and with the search of stop Ugolino on a fully hadronic final state. On the left, you can see the various signal models that have been considered, and in particular, there were for the stop, when there were the case where the stop decays on top of Nedolino or in a Bichargino, and then the Bichargino decays in a double Nedolino. In case where the splitting mass, difference mass between the stop and Nedolino was lower than the W mass, was also considered the possible decay with the stop in a charm than Nedolino. For the case where we have instead the splitting mass higher than the W mass, there was also considered a mixed decay mode where we have the stop one decaying in top Nedolino or the stop one decaying in Bichargino with a Banksy ratio for the two decay of the 50%. The Ugolino production instead looks at Ugolino that decays in a pair of top quark and Nedolino with an off-shell stop one, or mixed decay mode where we have also, together with the previous decay mode that I mentioned, also the ones where we have the Ugolino decaying in a top Bichargino or top B Nedolino. They were assumed different splitting. There was assumed a splitting mass for the Bichargino Nedolino equal to 5 GeV for these cases. And then finally, the last models was the Ugolino decaying stop on top, where the stop then decays in a charm Nedolino. And here there was assumed a splitting mass between the stop and Nedolino of 20 GeV, because in this way they can be possible to cover higher stop masses than the models where we had the direct production stop one that decays in charm and Nedolino. So two different the approaches were used depending on for what concern the stop one analysis, depending on the mass, if the splitting mass was above or below the W mass. So if we start when the splitting mass is lower than the W mass, so the low, we call this low delta time analysis strategy. Here we require, there's been required an aster jet, and they were defined different categories based on the presence of the secondary vertex or the B-target jets. Then they were looking at different slices of TT for the aster jet, the B-target jets, and also the transmissing energy. On the right, there is the diametral comparison for the various signal regions that have been defined. As you can see, there was no significant excess. So also for this reason, there was exclusion contour plots have been performed. And here you can see for the three different signal models that have been considered, how which regions were excluded, and were able to reach exclusion for small delta differences up to 600, 700 GeV for the stop mass. For what concerns instead the case where we have splitting mass with the stop Nedolino higher than the W mass, in this case, the categories were based on the presence of B-target jets, top target jets, or W target jets, and the number of residual 3 jets, so jets that were not flagged as a top or W candidate. They were looking at different slices of the scalar sum of the jets PT or the PT of the B-target jets and the transfer missing energy. And here on the right, there is also an example of some of these signal regions. And you can see there was no significant excess, and also in this case, some contra-exclusion plots were performed for the various cases. And you can see here that there is an exclusion that for the stop mass close to 1,200, almost 1,300 GeV for the case of the stop to top Nedolino. In any case, they were able to reach 1,200 GeV of exclusion for the stop mass for low values of the Nedolino masses. The same analysis has been also reinterpreted for the Ugolino models. And here you can see that on all they were able to reach almost an exclusion for the Ugolino masses up to 2,200 GeV. And in particular, I want to focus on the third case where there was this, you can see that respect to the direct search where we have the stop for decaying in charm and Nedolino, this analysis was able to extend the area of exclusion thanks to this new way of considering a stop decaying in charm and Nedolino after the coming where the stop is coming from the globino. Another search is the one for the stop is the one that looks at the two leptons in the final state. Here we have the same signal model that we considered in the previous search, plus the addition of third signal model where we have a cascade of SUSY particles. So the stop one goes then in a chargino, then in a lepton, then in a neutralino. In this case, the mass of the chargino is said to be the average of the stop and neutralino, while the mass of the lepton is a combination. It depends on the splitting mass of between the chargino and the neutralino, and there is a free parameter that is set to 3 different values. So in a way that we could have a different signal models also depending on the lepton, on the mass of the leptons. The analysis strategy was looking at the request of a gene epitome significance, and the categorization was based in terms of MT2, and in this MT2 BL, where therefore the product of the decay of the visible particle were considered not only the leptons but also the B jets and epitome significance. There were no significant excess observed, as shown in the plots on the bottom right, and also in this case there were performed some the exclusion control plots, and you can see here that we were able to reach exclusion up to 900 GeV for the stop mass for lights and everything. The same, so also for the third signal models, there was an interpretation. Here you can see how the counter exclusion plot change with the parameter Higgs that was defined the mass of the leptons. This here you can see as soon as with the splitting mass between the lepton and the neutralino is small, the sensitivity decreases because we expect in the final state soft leptons. And so we have a lower sensitivity for this specific signal model, as you can see from the right to the left. Again, for the stop search, another dedicated analysis was the one targeting the corridor that is here highlighted in the picture on the left. Here, the signal models are considered the ones where the difference in mass between the stop and neutralino is in a window with respect to the top mass of 30 GeV, and we are considering a stop mass lower than the 275 GeV. The final state is always with two leptons in the final state, and then there is the request of at least 2 jets with at least one of them be tagged. And usually, since the kinematic of the signal models and the study and is close to the ones of the TT bar, the requests on the missing transfer energy of the MT2 are usually lower than what is one will could ask in the bulk region, where we have a difference with the stop and the neutralino that is quite much higher than the top mass. So there were, in this case, the idea was to use DNN technique, and the training was performed on TT bar and different signal models, selecting only electron and mu events. In this case, there were several variables that have been considered, or characterizing the leptons, but together with MT2 and missing energy and so on, but also it's important that were considered also variables like the masses of the stop and the neutralino. And for the background, instead, they were decided to avoid any bias to put a random masses for the evaluation of the training. In this case, it was possible to have a different DNN score depending on the signal models and the study. And this different DNN score for sure is also for both signal and background, as you can see from the plots on the left. There was the combination of 9 channels, 3 delivering period that saw the years 18, 17, and 15, 16 together, times the 3 lepton flares that are left that were not used for the training. And then there was the binning of the DNN to enhance the sensitivity, because also in this case there was no significant excess. On the right, you can see the plots with the full area that has been covered and excluded by CNS. So, given that all the signatures with the 0, 1 the signatures with the 0, 1, 2 leptons have been addressed, CMS has done a combination of these three searches to enhance the sensitivity. You can see in these three plots that in general there is an enhancement in the sensitivity. And usually the 0 lepton search shows the largest sensitivity in the free case, and then the 0 and 1 lepton searches is competitive when the different mass within the stop and neutralino is small. If we do a comparison with the Atlas search, usually you can see that CMS is performing slightly better than Atlas for the large mass difference, profiting of the many categories, the findings, but also from the combination. Usually, while close to the top diagonal for the high value of the stop mass, the Atlas 2 lepton search performs better than CMS, and this was done thanks to the supervisor variables that have been used. While and this was only possible for this variable because with the MT2 variables was not possible to go so close to the top diagonal. In the corridor, Atlas and CMS have two completely different approaches. The DNN technique for CMS and the measure of the different cross-section for Atlas, but in both cases, there was a really good sensitivity. And in general, in the free body regions, Atlas shows a higher sensitivity, thanks to the, again, Renner analysis strategy. And in the for body region, both Atlas and CMS show similar sensitivity in both cases, thanks to the soft betagging technique that was considered. So going to the last search of CMS, here the final state was with two opposite signs and favor leptons plus large TMS. The signal model considered the ones where we have an gluino that decays in a pair of quark and a neutralino. And then the neutralino decays in a gravitino and a shell Z. And while the other two models, the one where we have a boson per production, a score per production, where we have this boson on the score decaying in a neutralino, 2, and then another 2 that could decay in as leptons or an off shell Z and a neutralino. As here we have two different signal models where one could have an on-shell Z, an off-shell Z, or an off-shell Z. So two different approaches have been followed. For the gluino search, the leptons pair with the invariant mass close to the Z mass have been selected, and the categorization was based in terms of jet beta multiplicity and was binned in PTMIS. For the boson score search, instead, there were the lepton pair were selected with invariant mass outside the Z mass window. And there was a categorization in terms of BVITO, beta J, and also TT-like events. It was constructed like with discriminant, so it was able to distinguish between TT-like and non-TT-like events. In this case, the final signal was binned in MLL. There are some plots to show the Monte Carlo comparison, and you can see here there was unfortunately no significant excess, and also for this reason, also in this case, counter-exclusion plots were performed. You can see here the reach of the area that was excluded for the 3 different signal models that have been considered. So moving now to Atlas. Here we will focus on a signal model where we have a production of the gluino that decays again in a pair of quark and a neutralino, and then neutralino that could decay in a Z or a gamma or an X boson. In this, and then a gravitino. In this case, the gravitino mass is sufficiently light to ensure a prompt decay of the next to the lightest particle. And the branch ratio is assumed to be always the 50% for the neutralino that decays in X, gamma, or Z, or plus the gravitino at the end. So there were 2 signal models at the end, as they are shown here on the diagram on the left, that were considered. And the final state is characterized so with a photon and high jet multiplicity. There were 3 different strategies to target signal models with the large, intermediate, and small differences in mass between gluino and neutralino. And usually there was an increasing, usually for the find this region, increasing in the request of the PT of the photon, and increasing the request of the missing transfer energy or the scalar sum of all the jet PT that we have in the event. The best expected sensitivity has been considered also in this case because also here there was no significant excess, as you can see from the plots on the left. While on the right, you can see the final counter-exclusion plot, where you can see that we are able to reach sensitivity close to 2,300 GeV for the green masses in both signal models that have been considered. So moving to the stop-to-star search for others, here we have the signal model is the one where the stop is decaying B neutrino and a stop. And then the stop decays again in a top and gravidino. The gravidino mass, again, also in this case, is considered sufficient light to ensure a point decay of the NLSP. And the analysis strategy is the one that we have characterized by at least 2 jets in the final state, with at least 1 bitarget jet, the presence of tau, and large missing transverse energy. 2 different signal regions have been defined based on the number of taus. The D tau channel, where we have 2 opposing sign taus, and the signal region is based on the MT2, and a single tau channel, where we have at least 2 beta-gate jets. And the signal region is based, definition is based on the scalar sum of the transfer momentum of the tau, the 2 leading jet, and the tau transverse mass. And this has been in PT of the tau. There was also here, unfortunately, no significant excess, as you can see from the plots on the left, for the 2 signal regions, the D tau on the top and the single tau at the bottom. And the analysis was and also the analyzer have performed the counter-exclusion plot in the stop star mass plane. As you can see, there was an enhancement in the sensitivity with respect to the previous round of analysis. This analysis was also reinterpreted in the leptowork models, and this was shown last month by Alexander Mas. Another search is the one where we have as bottom that decays in B and neutrino 2, and then this was at the dimension at the beginning, where we have an Higgs boson that then decays in at tau. Here it is assumed that the difference in mass of the neutrino 2 and neutrino 1 is equal to 130 GeV, and we are assuming that the Higgs boson is the standard mode Higgs boson. So the final state is characterized by 2 opposing sign taus, whose invariant mass is between 55 and 120 GeV, and at least 2 beta-gate jets. Large values of MT2 and large values of the scalar sum of the momentum of the jets and taus. And the signal region definition was based on the minimum solid angle of the 4 combination of the 2 leading taus and the 2 beta-gate jets. We expected that this theta min is shows small angle when the tau and B come from a top quark, while we expect to have an increasing of this angle with increasing the mass of this bottom part. Of this volume.
3 minutes.
Okay. In the left, there is the plots showing the data multivalue comparison. You see also here there was no significant excess. And but on the right, there is the final counter-exclusion plot. You can see the enhancement in the sensitivity, and this enhancement with respect to the previous round analysis, this enhancement is essentially due to the change of the different final state that was considered for the analysis. Going to the last search, the one with the bottom to be this bottom production, we have this bond decay in B and Adalino. Here we have 3 different analysis strategies depending on the target's difference in the models that have large values of the splitting mass with this bottom and Adalino, or intermediate values or small values. And the ones with the large values for target the signal model with a large splitting mass, the definition of the signal region was based essentially on the controversial mass. And while for the intermediate case, there was the idea was to select either to construct this signal region to be orthogonal with respect to the signaling array, thanks to an upper count of the MCT variable, and then to define a BDT, with a multi-classification procedure. And for the exclusion, it was also possible to do a binning in BDT score to enhance the sensitivity. While for the small values for the signal model with a small splitting mass, the idea was to consider the NSRJ to enhance, to boost the system, and then to define three mutually exclusive signal regions based on the number of beta gadgets and the presence of secondary vertex. And then there was, for exclusion, there was considered binning in a missing plasma energy. Here on the left, you can see the plots for the free signal region that have been considered and with the various bin. And then there was again no significant excess. So for this reason, at the end of the SRA and the SRB were combined together, and the best expected being the combination of SRA and B and SRC were selected for the final counter exclusion plot. This is shown here on the right, where you can see the increase in the sensitivity. So going to the conclusion, I even show you only the recent results for both experiments. There was a broad and solid program. It's like we are looking at the needle in a high stack, and so for this reason, both FADR and CMS have increased their sensitivity thanks to new reconstruction technique, machine learning, the use of the machine learning technique, the implementation of new variables like the PTM significant, this TT-bar like discriminant, and the combination of different analysis or looking at the new signatures. Thanks a lot for your attention.
Okay, thank you. Is there any questions and comments? Please.
Hello. Do you have a exclusion plot in the Skog mass and Gruino mass plane?
No, not neither in backup. I have this information.
Are you going to make such a plot?
For the analysis that we've seen up to now, I have not seen these plots, but I don't know if the analyzer are willing to do it. So these are, I don't know.
Okay. I recommend you to make such a plot. Okay.
Okay.
It has some meaning. It has some meaning. So I recommend you to make such plot. First and second generation Skog mass, horizontal line, and the vertical line is a Gruino mass. And this is a simple Gruino, Skog, and neutralino model. Okay.
Okay.
Yeah. Please try using new data. Okay.
Okay.
Yeah. Thank you.
Okay. Thank you, Longo. We move to the third talk we just missing. The speaker is Richard Bazzini, talking the other searches.
Okay, thank you so much. Thank you, and my full apologies about my being late. There was a mix-up in my Indico setting in the time zone, so I was 1 hour late. Okay, so I will just share my slides now.
Can you share?
Yes.
Your slides?
Just one.
Okay.
Are they in a full screen mode or not? No. No, yes. Okay, thank you. So, okay, thanks again. And so I will be presenting here a combination or a brief summary of Atlas, or some of Atlas and CMS searches about some physics processes that were not covered in the SUSY, Higgs, or dark matter talks in this conference. Just after a brief introduction, so as all you know, LHC12 is actually a gold mine for physics studies because we have a very large data set with well understood detector performance. Along the line, there were many new techniques that were being developed, optimized for background estimation, signal enhancement, and so on. Mainly consisting from improved boosted object tagging, for example, high performance machine or deep learning approaches, and so on. Both the CMS and Atlas continue to provide high precision measurements because the run-to analysis are still in full production mode. So basically, a lot of measurements for standard model processes that helps to determine fundamental parameters, probe higher order QCD and electroweak effects. And in conclusion, so far, most of these results goes well beyond the standards set by the LEP and Tevatron era. So these measurements or these high precisions actually allow us to access for the first time some very rare or poorly understood processes in the standard model sector as well. So there is a broad search program at the TAFE scale and beyond. And this can allow us to investigate the existence of some very weak or ultra-weak interactions that could help to address fundamental questions in the standard model descriptions. About run-to data itself, so both Atlas and CMS have collected an impressive amount of high-quality data from proton-proton collisions at 13 TeV, center of mass energy, in addition to the heavy ions collision programs as well. So you can see from these two plots the quality of the data collected and used in physics. Here in this talk, I will be presenting only a subset of results, mostly recent ones from non-Higgs SUSY dark matter searches. The full list can be found here both for Atlas and CMS for people interested to go beyond what has been presented in this conference. I will start with one of the first topics that basically everybody was searching for. Many models predict some kind of diboson resonances, either extra dimensions, the heavy vector triplets, little Higgs models, and so on. And these dibosons or this any resonance can be produced either through glue, fusion, Drellian, or VBF as presented in these three diagrams here. They can decay either to VV or VH resonances. For a more extensive review, so one can actually check this link for Bill's presentation. So starting with a very simple resonance, basically if we have a high mass W, a W prime that could decay to a W and H, we did that going to electron and neutrino, and the Higgs to a BB bar pair. So basically because of the possible boosted object, so the analysis use either merged or resolved Higgs boson decay to categorize the events, in addition to one or two B-packed jets, as you can see from this diagram here. So in this plot on the right side, so you can see the effect of combining both the merged and the resolved configurations in order to gain acceptance in the OR signal for this. And this is shown here for the different B-pack categories. Okay, so the MW was used to constrain the constraint for the and in total the invariant mass of the boson and the Higgs is used as a discriminant variable. Of course, once all of these things have been done, all the different backgrounds have been correctly estimated, and the main one are coming either from top W plus heavy flavors or a W plus jet. One can actually cross-check these background estimations against the model, the standard model predictions, and then do a global fix in order to extract actually the significance as a function of the W prime masses and compare it to the observed data, which is shown in this left-hand plot. So basically, you can see the expected, the full line showing the expected, the observed limit, while the dashed line is the expected limit, and mainly the observations fit within the plus or minus 1 or 2 sigma, depending on the Higgs mass, the W prime mass considered. So the limit we reach is about, depending on the model we are using to compare to the data, is around 3 TeV exclusion actually for these two models here. Similar things can be done if we consider the coupling to fermions as a function of the Higgs and vector boson coupling GH. So you can see the exclusion limits can be actually put in this plot here, depending on the decay and the masses and the different width and masses that are considered here. So you can see that most of the parameter space is excluded except these very small regions here that is currently not excluded with our data. So going further with other diboson searches, so either looking at the boson plus a photon with the boson actually decaying to a pair of jets. So the jets can be actually either resolved and or boosted. So both CMS and Atlas did these searches for resonance decaying to a vector boson plus a photon. So in CMS, they looked at the W gamma with generic searches with merged jets and the central photons, and then they managed actually to reach to extract actually the current limit that are shown in this figure here, the bottom left one. So you can see that mainly the observed limits correspond to the expected ones within the plus or minus 1 or 2 sigma at 95% confidence limit. However, there is some small excess that they observed around 1.5 TeV or so, and then depending on which approach, either the broad or the narrow approach, they see between 3.1 to 2.8 sigma excess around 1.6 TeV. The global significance itself is around 1.7 to 1.1. Atlas did something similar, but for both for W and Z, using boosted hadronic decay. The events are split into orthogonal signal regions in order to separate the two bosons, to do vector bosons, and the infinite likelihood of balance is used actually in each region. There is no significant discrepancy with respect to the standard model, and as you can see from the bottom right figure here, so the observed limits are within the plus or minus 1 or 2 sigma bands, as you can see here. And this actually allows to set limits over a wide mass range, and also to consider different models for the resonance that is being searched, either spin 0, 1, or 2, depending on the models that are considered. So this plot is for V gamma, and the similar limits are exist also for the W gamma. Okay, so this is for the diboson. So CMS did the first diboson searches by looking at this particular process with the decay of to a radion and the W, and then the radion decaying to the W. So in the end, there are 3 Ws in the final state. This particular model has been exist in either extended drought extra dimensions, which enhance diboson projections, and so. So basically, only the electron weak is extended Berk dominant in this particular model with the radion decaying to 2W. So It can be either a resolved radion as seen here, or a merged one as seen in this particular plot. And then they manage actually to reconstruct actually this particular event configurations as well. By looking at two W tagged massive jets in the W in the VV new region here. So basically, the CMS managed to do the correct background estimations. As you can see here, this basically dominated by W plus jets or TT bar, and comparing to the data with some signal that has actually is simulated here as well. So in the end, so there is no particular excess with respect to the standard model prediction for these three boson searches. They put a first limit on this WKK to radian W with 3 W's in the final states, and on the resonance mass and the radian space, mass space with a combination of semi-electronic and hadronic final states, as shown actually in this figure. Okay. So next is something that is very, very interesting in this field. So basically to look at the flavor change in neutral current in the top quark sector, as the top can open many possibilities to physics beyond the standard model. So it allowed the FCNC allow for transition between quarks of different flavor but the same electric charge. They are highly suppressed in the standard model due to the GIM mechanism, but they have a very small contributions appearing at the one loop level. So both CMS and Atlas explored this FCNC, the top sector, via the THQ process with the Q either an up or a charm quark. And they using different Higgs decay modes, either so CMS used diphoton, Atlas had CMS BB bar, and tau tau in the Atlas scale. For all of these final states, the dominant background is basically either resonant through TTH or VH and this list here, or a non-resonant background, either coming from TT bar or a vector boson plus inclusive vector boson productions or QCD. Signal regions are categorized for maximal signal sensitivity depending on number of jets and number of B jets, and several strategies are used actually for signal to background separations, either PDT based or likelihood based discriminant. Starting with CMS. So they searched to an effective Lagrangians with this right-hand hand coupling that could actually include an FCNC mechanism. Upper limits on the signal cross-sections are translated, of course, to the strength of the TKH anomalous coupling and related branching ratios, and they have actually produced these results for THQ with Higgs decaying to diphotons or Higgs decaying to BB bar as shown in these two plots. And then they can compare actually their expected significance with respect to the observed one in the branching ratio of TH decay to HC or T decaying to HU. Similar things is also in the H2 BB bar final state. So in conclusion, from their studies, they managed to set an upper limit of these two particular decays, which is around 2 times 10 to the minus 4 for T to HU, and 7 to 10 to minus 4 for HC. And this is something similar results actually coming from the other decay rate as well. Okay, so this is from CMS. Atlas did something similar. So basically searching for the same FCNC in the top sector by looking also for through the Higgs to BB bar and the Higgs to tau tau failed states. The results, Atlas results, use 36 inversion to 1, and they combined other results from Higgs to gamma gamma, WW star, tau tau, and ZZ star in the final states to the different lepton content and combinations. Okay, so the plots here show something similar thing. So basically, for each of these final states, you show the limits that are actually set before the combination, and the combined results from all these channels is shown at the bottom of these two plots here. So you can see that this is something that actually Atlas managed to have, and the limit is mostly compatible with the standard model predictions as shown in these two plots here. So the combination is again shown here, and there is no significant excess of event above the background's expectations as well. So the combined results from all these the Higgs final states are actually shown in this, and they are mostly compatible with the standard model predictions, which is this dashed line here. Okay, so as a summary, so there were various channels that were used to probe the FCNC signatures, and they are all combined in these figures. What is mostly interesting is the following. So the solid line shows actually what is coming from the standard model predictions here, while the different colored area are actually showing the limits that are coming from different models that are actually shown in this, that are described here. So these models are still far away from the current limit, except from this, the ones that produce a higher branching ratio, and these models can currently be tested with the current limit from Atlas and CMS. So it will be possible actually to test this, to probe these models that are providing this highest branching ratio and put in actually limit on their predictions and parameters. So there is also another sector that is actually being studied both by Atlas and CMS, which is the lepton flavor violation in the top sector. And this is done through the way of looking at TT bar events and looking at different top decay that can produce a lepton flavor violation in this sector. So basically, but looking at a top decay into two lepton with different flavors. So there are three types of lepton flavor interactions that can be considered by an effective Lagrangians here. So they can be either a vector, scalar, or tensor, as shown in this interaction term here, and they can be actually tested as well against the measurements. So CMS did this study. So basically, you can see here by looking at the BDT discriminant for these particular searches. So there is no excess with respect to the data. So the data is compatible with the standard model predictions for the background processes within this search. And then again, once this can be translated into an exclusion limit within these parameter spaces here, and comparing them to the different lepton flavor interactions, either scalar, vector, or tensor, you can see by looking at the full line or dashed line that the measurement observed limits are compatible with the predictions from the standard model. So this is in this case. There is also a lepton flavor in Z boson decay. This is work done by Atlas. As we all know, so the lepton flavor violation is only observed in neutrinos, but it's very negligible in charged leptons in the standard model. LCRN2 has produced a huge amount of Z bosons, and they can be used in order to look for Z decays into different flavor leptons. Like in this case, Atlas looked for Z decay into E electron and muon, or an electron at tau, and they looked actually for an excess with respect to the background estimation from the standard model processes. So both E mu and E tau has been used. They have actually used different techniques in order to to do the estimations. And then you can see from this plot here, the invariant mass of the electron, the 3-electron muon, or the invariant mass, the invariant mass of the electron muon in the left plot here. So you can see a possible decay of electron flavor violation here, which is doesn't appear in our data. So the data is mostly compatible with the background, the estimation, as well as the combined neural network output. This is for the mu tau final state, and again, the data is compatible with the standard model predictions for this particular decay. So using all this, so Atlas managed to extract these limits on the Bayesian ratio for Z to E mu, Z to E tau, or Z to mu tau. As you can see by comparing this column here, that the limit set by Atlas is actually much constraining than the one that are coming from left, for example. So in conclusion, so the Atlas results improve this limit by a factor of 5 and 2 depending on the final states, and this actually it is a full improvement and a strict limit on this particular process as well. So the next item is vector-like quarks. So they are important signatures in many BSM models. They consist mainly on colored spin 1.5 fermions, but their left-right-handed complement transform the same way under gauge transformation. They can be partnered to standard model quarks with the same charge, or can have a more exotic charges. In simplified models, the VLQ mix with the standard model partners to regulate the Higgs boson mass, and they mix predominantly with the third generation standard model. So this is they can be produced either in pair or in single projections, and they can decay through their standard model partnered with this Bayesian ratio here, depending on the model value. Okay, there's a broad search program in Atlas and CMS using full run 2 data with different new techniques and so on, as I said before. So starting with the vector like top or B, Atlas actually searched for for this particular decay, and in addition, so in this particular decay, and in conclusion, so masses of VLQ above 1.9 TeV are excluded for this coupling parameter. So we'll skip this. So in addition, CMS did a combination of W prime and TeV or BT as well. And then with the benchmark masses of 3.2 TeV, they can actually exclude both W primes and the corresponding VT. For lepton quarks is another possibility for new physics. I will skip this. What I will show is the Atlas combination for lepton quark, which basically used reinterpretation of S bottom decay, as you can see from these 2 plots here. So basically the limit from the S bottom decay and the limit limit from the S bottom decay and the limit for the lepton quark searches in this particular case. And the gray area is run 1 results. So you can see that from this reinterpretation, the run 2 limit is much more strict than the run 1. Okay. Beyond the 3 generations, so CMS did something similar, so I will skip this as well, and to go to the different generation coupling, which basically Atlas did a different coupling, so basically to look for a coupling through either C and B, and sorry, and as a conclusion, the Atlas managed to put limits ranging from 500 TeV to 1.6 TeV, depending on Bayesian ratio, as you can see from this plot here. Okay, so the last searches were consist on looking for seesaw heavy leptons. So they were actually they consist of extrafermionic triplets, either neutrals or charged ones, decayed into standard model leptons and the WZ or Higgs boson with the W with the highest branching ratio, several lepton gas configurations were probed, and you can see depending on the lepton finite states as shown in these three figures here. So Atlas managed also to set limit on the existence of the seesaw heavy leptons, rejecting or excluding masses below 910 GeV after combining the results from these three searches. So the last item in this talk is for fermion contact interactions. We can, as quarks and leptons can be composite with at least one common consistent, which is effective for fermion contact interactions at a scale lambda. CMS actually used this theta star angle of the outgoing negatively charged leptons as defined here. And once they compare actually this, the charge, negatively charged particle that goes with the standard model prediction background for these searches, they can actually set limits on these lambda parameters. And both Atlas and CMS have consistent limits around between 22, 23 GeV up to 36 GeV or 37. Okay. Finally, Atlas used an EFT approach to study the BSLL contact interactions, which can actually be related to the flavor anomalies in the B meson decay that has been observed in Bell, Barbara, and so on. So the difference for electron and muon can actually change this BSLL contact interactions at the scale and the coupling as shown here, and using the cumulative signal regions as shown here by estimating the different background component, they can actually explore if there is actually this possibility of this enhanced contact interaction for this particular finite state. So comparing the data to the backgrounds, Atlas managed to have actually a large observed local significance around 2.86 sigma, while the lowest limits range from 1.8 to 2.4 TeV. So as a conclusion, Atlas and CMS, they performed a tremendous effort to search for new physics beyond the standard model, and it's continuous and ongoing program. Numerous models have been tested and the predictions cross-checked against experimental measurements. So there is a more strict exclusions in the different parameter space of new physics, whether it is boson resonance, vector quark, or vector-like quarks, and so on, or also testing the existence of new interactions such as FC&C violation or contact interactions, and so on. So far, no observations of any significant difference with respect to the standard model predictions. And these ongoing studies actually keep using some new techniques that will allow for a much higher improvement in the different measurements and searches to explore the hidden corners of the standard model. Round 3, with the double of the current luminosity, will also provide even more data for more extended search. Thank you so much for your attention.
Okay, thank you, Richard. Any questions, comments? Please.
Yes. Could you comment on the last topic about the mu-E universality that you just rushed, and you talk about some significance, but I didn't understand well the point. Could you show this last slide, that slide 23, I guess?
Yes.
Yeah. Could you comment on this success that appears in the tail? So what is the significance you are talking about?
This is a cumulative significance. Basically, each bin is a accumulation of the previous ones, and so on. So this is what we call the cumulative signal regions, and then we can actually test if there is an enhancement due to particular, a new interaction or a new, enhancement of the interactions that can exist. And I mean, the fact that we have an excess here can also be, I mean, we have an excess of data with respect to the background estimation. Can also be the case that we don't have actually enough, I mean, in these regions, we don't have, our Monte Carlo doesn't go far away enough in the description of this particular region.
Excellent. Okay, thank you very much.
Any more questions? Okay, thanks, Richard, again. Let's move to the last talk of this session on SUSY, Chargino, and Neutralino by Teruki Kama.
Can you hear me?
Okay.
So can you hear me okay?
Yeah.
Okay. So let me start. So my task is the overview of the SUSY charging Newton search at CMS. So outline is I have a few small introduction for electric sector and followed by the CMS result on the charging Newton search. And in the bottom line, there's only one new result since the EPS workshop, which is work on the charging indicator WH, WG, WL in hadronic channel. And also, please see the talk for more technical details. And also, I don't cover for Slepton search. And all of this plot you can find from link below. And the three link from CMS, the blue is summary plot, and the link from Atlas, again, blue link is summary plot. And I give you a summary, the last slide. And this is the talk you can find in this conference. The left panel is the Atlas, and so left and right panel is the CMS. So now one slide for the electric sector menu, and it comes from the mixing of Vino, and Chargino. Depend this mixture and this derived indicator Higgs or WG also depends on nature of the recipe. The lightest neutrino K10, Vino, Higgsino, or Vino Higgsino combination, and that dictate the decay product on the mass splitting. Or if recipe is gravitino, that can be decayed to photon D and H. And also the nature of the lightest photon and dictates of branch ratio or kinematics, such as K2 decay to lepton and lepton, followed by lepton decay to lepton K10. And you have a sketch in the right-hand side. And also, you can bring in the right parity variation with K1 that can decay to lepton, depends on the coupling. And if mass split is small enough between charging neutrino, like 100 MeV, there will be pion and produce the spring track topology over long lifetime, or even you can consider heavy stable charge particle, or every can expand more for non-minimal or non-universal case. And the sketch in the bottom is showing for different types of decay topology. And the page 5, this is an expression map of SUSY, and you have PP cohesion and produce in parents, pairs, and cascade decay to lattice object with the standard particles. And often you see the result in the mass of parent SUSY particle and lattice SUSY particle in particle. And also particular structure in the result is the blue, it's the express large mass, and in this case, both the objective ID is important, or you can see very mass, complete mass spectrum. In this case, you need the low PT objective ID. And the sketch in right-hand side gets strong protection or weak protection, and my talk is focused on electric protection, and those depends on trigger and the breath analysis, which I can explain more. And the next slide is the instead of I give you data analysis, I just give you the one common theme on the all analysis I'm going to present today. And based on advanced particle ID and such particle flow boost the object. And we employ for the ticket simulation and also considering for single production and decay and characterize this define so-called single region. And also we define control region. So therefore, we can employ for brand analysis, which means we understand data in the control region fully before we look data in a single region. And once we understand, we look for the event in a single region. And this example for this, the production decay, and we have 64 single region for the charge and neutron production in the leptons, and you can this reference in this plot, and you can see the agreement with the observation prediction is very good, and you can also play expected signal in different color code. And let's pick up the green here. So you can see all of the region is accessed by the green. So you can look for multiple single region combined to maximize sensitivity. And example is in this course, you can see neural net, machine learning or deep learning, and the maximum sensitivity. And you put the neural net attitude, and you have nice agreement of the main magnitude of the scale, and see the look for signal in the particular output here. So this is the common analysis flow. And the next slide, I'm going to show summary of the results. The first is looking for charging on neutrino protection and decay to leptons through the right lepton. So this is the sketch of depends on where the lepton must reside. The reference plot result is choosing for middle of the two neutron mass. So that's called 0.5. And the result in the left is Earth and the right CMS. So there are a lot of information. Let me spend more time. And so this color scale atlas through the 30 investment one or 140 investment one, and the CMS is depends on 140 investment one. In the case of maximum reach, you can see in the lepton charge neutrino, and you can compare this result with atlas of the but the atlas CMS and reach up to 1.3 dB. The case of writer selectron. But if you choose the star dominate, so this is star instead of democratic selectron, and the reach is weaker, you can see around 800 GB and both case in atlas and the CMS. And of course, the other scenario such as the heavier selectron that reduces the branch fraction or mass, small mass difference is showing weak limit. So now, if you prefer for the star, the between, and the CMS, atlas CMS is for the ISR jet tagging, and the small mass difference in the 50 GB between Chi2 and Chi1. So that means star is between, so star and the Chi1, 0 is 25 GB. And so the tower D is like 20 GB. So final state, even if 3 tau, and luckily 12.3 is missing below threshold. So important to SRZ, the 1 tau analysis, so we can see the reach of the charging mass unit mass is about 300 GB. The mass spectrum 50. So that's important for this particular point here. And on the atlas plane, and this is the star result. And for CMS, this is the point, and this is the result. So that means SRZ is the useful compressed machinery. So moving to the decay to WH in the term the SUSY to be or run lepton to be. In this case, we employ for the large radius jet ID for tagging to jet or to be for the tagging W, G, or H. And again, the atlas result left and the CMS result in the right. And this new for this conference. Let me compare for SUSY to be result for CMS and this reach and atlas and the CMS is reach. So you can see about 1060 GB atlas, which is the above expectation, and the CMS 950, this is below expectation. But if you look for expectation, the both are very similar. And this, the case of lepton to be, atlas is 750 and CMS 820 here. And of course, as a decay channel, is a smaller branch fraction and showing weak limit. In the case of WD, so you have a 2Z2B or 4Z or leptons, and the corresponding is a WZ tagging 2Z or Z tagging BZ. So now the legend in the scale box is new for this page, and the case for WG in the 2Z2B compared to the WG 2Z2B in the right hand side. And limit are 960 GB for atlas and symmetry expectation. And CMS is 860, this is below expectation. But expectation both are the same, similar to both cases. And if you look for the compressed scenario, you have to employ for such lepton that you can see the atlas this region here and compare to CMS this region. And the further compressed scenario, the rear on the very soft electron tagging, and you can see the case attached here and the same here, reaching to around 300 or 50 GB. In the case of WW, so this case we employ for jet search or Triton. And the case of this is Atlas in left and CMS right, and Atlas has for jet and the Triton search, and the CMS has for jet search, which is new for jet conference. And reach for maximum reach, it does exclusion for Atlas is limited between 630 here and 760 here, because they apply for effective mass basically hadronic effect activity the greater than 1.2 dB. So that's the limit of this low mass region, but the maximum sensitivity. In the case of at CMS, that's on this requirement and the broad exclusion from about 300 up to 670 GB. In the case of the lepton, the CMS doesn't have the Atlas has the explore low mass region, so it's comprehensive. Now, the case of you see now result with the very mass splitting between chargino or Newton 1 and the Atlas in the left and the CMS right hand side. And to compare, we have to based on this template in the top left, the Atlas there is mass difference between chargino 1 and the Newton 1. And seems to find Newton 2 and Newton 1. So if you look for this particular mass point charge 1, Newton 2, Newton 1, for this number, translate the 205 in the Atlas and 205 and then in the CMS, which you can see very similar result. And also you can notice in this region of the 150-10 or 160-20 CMS is a result of that rim. excuse me. Of the rim is below expectation, both alto CMS and S region, and particularly around the direct mass, and you can see the spectrum summation in bottom right. In the case of the we know that's endpoint, but the signal is very broad, so any fluctuation data on the lepton, and that's causing for the observations below expectation. So now, as a complex machinery suit WG, and CMS Atlas has the full data set, and the CMS 36 in the Smithon is a vector version tagging with the lepton and the one lepton. And the Atlas is for two lepton final state with the isolated tagging and the vector version. The point here is the both experiment reach very low mass region around 1 to GB and also above the lab limit. And this could also expand down to around 0.5 GB, hopefully. So now, change gear is a mass splitting between charging Newton 1 is small, like 100 MeV. you can produce the pion very soft. That's called the topology for so-called this bearing track, or even you can look for heavy stereo charge particle. And the result in the other left and CMS right, and look for this particular point here, and the both are around 900 GB for the lifetime 1 or 2 nanoseconds. Or even you look for heavy stereo charge particle, and others useful such as investment one, and the reach about 1.1 TB. And CMS does the same product, but using for the right side and used for about 10 investment one. In the case of gauge media scenario, the mass limit start is 60 GB. So we are exploring for the many different topology and setting higher limit. Now, case of graphene LSP, then you can find for G and Higgs, and the case of mass generating signal case, and this limit is shown Atlas left and CMS right. Atlas made a comprehensive search for B finding state and true for lepton, and the lepton the mass and the branch fraction, so they cover for large area. And the CMS has Higgs finding state and the set limit around 1 TB for both if branch fraction to graphene Higgs is 1. However, you can notice particular region here, and this is mass between 30 and 90 GB. It's not the excluded by trust, but same point, the CMS has excluded this point. So this understand the fluctuation for particular data set. In the case of alpha-T variation, and depends on coupling, and you can have 3 lepton, 1 lepton jet, and 3 jet. So therefore, such a strategy is for number of leptons, number of jet. In this case, the others improve for 1 lepton and 2 number jet of B, or 2 lepton and number of jet on OB. First, mark the use neural net to maximize. And the result into particular scenario gets Higgs less P. So mass is the degenerate, and in this case we know P, of course charging and chi-1 and coupling a particular coupling for such generation or second, which we can limit from as explained is for 3, 2, 3, which limit you the clock doublet, so top and B, and the singlet second generation, that the strange clock.
3 minutes.
Okay, and this third generation singlet for this big clock. So therefore, this case top strange B, or you can be strange sub. And the limit are around 300 GB or 320 both case. So just start for the comment on the round 3 and beyond. And if you can see the link I presented I tried, you can find the projection. Since this is electric search, so therefore I put this others that you see now, and WG in the CMS, And the reach was around 50 GV of current surge can be extended about around 350 of close to 400. And also phase 2 detect pressure ongoing that maintain current strength could be enhanced for particular search, such as timing capability that will be available other things. So last summary. So I present for the electronic search in the SUSY for 140 in the 21, and this is the bar chart, and the prior you don't see details, but you can see the 1 TB lines here and here, and the problem for the mass around TB in the very diverse such scenario, and including more compressed, more challenging, like compressed mass, long lived, and heavy charge particle such. And also remark that there is more mass coming in the rest of year, and the higher energy, higher luminosity is to give us chance for look for hopefully new area before the new idea you can prove. Thank you so much.
Okay. Thank you. Is there any questions? Please.
Hello, I have a question.
Yes.
For neutrino charge search, you assume the second neutrino decays into Higgs and the lightest neutrino. Okay. And in this case, do you assume 100% branching ratio of secondary neutrino to Higgs and neutrino, lightest neutrino? Also, Higgs to BB branching ratio is 100%. Do you assume all 100%? No.
The Higgs is a standard motor, so it's a decay to the BB is 80%, whatever number of standard motor. And for this particular search you present in the particular branch fraction, and you can see we can assume 100%. So therefore you have a particular scenario where the branching fraction smaller and the weak limit is getting weaker. And the other sense gives template, so therefore you have a particular scenario in the branch fraction, you can estimate the limit on your case.
Okay. For Higgs to BB, you assume 80% branching ratio?
Java, this is a standard motor branch fraction.
Okay.
And of course, if you have different Higgs particle, then story different. But this is the simple W boson and the standard motor Higgs decay.
Okay.
Okay.
Okay. In some case, at one loop level, Higgs to BB branching ratio changes significantly at one loop level. In MSSM, Higgs to BB decay branching ratio can be different from standard model value significantly. For example, deviation is about 30% or so.
Yeah, then
have to be careful. Have to be careful.
Yeah, but again, message here about the assume for the standard Higgs data limit, and then you can contact CMS address this is branch fraction. We can re-estimate the limit. We can do that.
Okay. So, okay. In any case, we can reinterpret your result depending on the model, SUSY model.
Yes, that's the purpose of data CMS.
Yeah. Okay. This is the typical limit.
Yes.
Okay, I understand. Thank you.
Okay. Carlos Wagner. Carlos.
Oh, I apologize. I was muted. So my comment is directly also regarding assumptions that you do in the analysis. So then my interpretation of this is that you are using the Wino production cross-section. And the Wino production cross-section, as you well know, Teruki, has a T-channel contribution that depends on the square masses.
Yes, that's true.
Then I guess that here you assume Wino production cross-section with very heavy square masses.
Yes.
Is that right?
Yes.
So, but the cross-section, actually the T-channel production cross-section has a negative interference.
Yes, that's right.
And therefore, that will be good to remind in the papers that this is the case, that you can weaken somewhat the limit, assuming that the squares are 2 TeV instead of, for instance, being totally decoupled. And that effect is relevant, so it's somewhat relevant. The other thing that is related to the previous question is that if you have Winos with a significant mass difference with the neutralino, they tend to decay into Higgs, as you here assume. So then it's almost 100% into Higgs for the neutral Wino compared to Z. And therefore, when you do in the next slide, you project the limits also into Z. So the Wino decay, the neutral Wino decay into Z and neutralino. I think that is somewhat unrealistic. That never happens. Then in the Wino cross section, in the Higgsino, of course, it happens because the branching ratio is 50-50. But again, that has to be taken into account. But one has to differentiate. So if you assume the Wino cross section, you have to assume the proper Wino branching ratios. So we can discuss if you want, Teruki, in private.
Yes.
Okay.
Thank you.
Very good. You're welcome.
Thank you. I talk to you soon.
Very good.
Any more questions? Okay, if no questions, we thank Teruki and all other 4 speakers of this session again for your excellent presentation. Now we close this plenary session. Thank you all. See you.